What's up, everybody? This is Mr. Prevet going through the 2024 FRQ number 4. So far on this year's FRQ, we've seen some accumulation functions, some particle motion, some differential equations, and now we get to see a lot of applications of integration, especially in terms of relating to this graph. So I'll have the graph over on the left side. So even though I may not have it drawn, hopefully you're rocking with me. We can kind of piece this together as a team. But let's read question number 4. So it says the graph of the differentiable function f shown for x is between -6 and 7 has a horizontal tangent at x is equal to -2. So we know that f prime of -2 is equal to 0 and is linear for 0 to 7 for our x values. So kind of once we get past that region R that's shaded in, the function is just linear. So our derivative should be constant that entire time. Let R be the region in the second quadrant bounded by the graph of f, the vertical line at x equals -6, and the x and y axis. It tells us region R has area of 12. So, okay, let's go ahead and get started with part A. So we've got this very interesting function that seems a little bit contrived, They're creating this region R. Like, this function wouldn't exist in real life, but they have created it for us. But part A says that the function g is defined by g of x is equal to the integral from 0 to x of f of t dt. And it asks us to find a few different values: g of -6, g of 4, and g of 6. So it asks us to find these values. So one of the very important things that we do need to understand about integrals is that when my integral goes from a to b, and I go from a large or a smaller number to a larger number, the integral of that function will give us the area under the curve. So for instance, our integral from -6 to 0 of f of x would give us just the value of r, which is equal to 12. And that's actually going to help us for this first one. So g of -6, that is the integral from 0 to -6, f of t dt. Now, we don't really have a great way of solving this integral, but we know that when we switch our bounds, we negate the value of the integral. So this is equal to the negative of the integral from -6 to 0 of f of t dt. And this integral represents the area of region R because it is the definite integral of a function above the x-axis. That'll represent the area. So we know this area is equal to +12. So this integral is equal to -12. So boom, we are done with our first one. I kind of assume I can look at the rubric real quickly, but I assume that each of these parts was worth 1 point. It was. So we got 1 out of 3 points so far. So let's move on to the second one. The second one is g of 4, which is equal to the integral from 0 to 4 f of t dt. Now looking at this function, our integral from 0 to 4, the function is still above the x-axis, right? It creates that triangular shape, and we know that we have a definite integral of a function that's above the x-axis, so it's just going to be the positive value of whatever the area is under that curve. So we have a triangle, so it's going to be 1/2. Our base is equal to 4, and our height is equal to 2. These 2's will cancel out, and we will just be left with a value of 4. And that is g of 4 because we know definite integrals of functions that lie above the x-axis is just the area under the curve. Okay, so we got super easy so far. We're 2 for 3. And now our final part, g of 6. This will give us the integral from 0 to 6 of f of t dt. Now, when we look at the function from 0 to 6, it's still that linear function that we've seen earlier, but now there's a portion that's going below the x-axis. And this is where it's important to remember when a function goes below the x-axis, its definite integral will contribute negatively towards the integral. So this function is going to be the positive of all the area that is above, which we calculated to be equal to 4, that upper triangle, minus all of the area that is below the x-axis, which is that triangle from 4 to 6, which has an area of 1/2 times our base, which is 2, times our height, which is 1. And those 2's will cancel out. We will get that the area of that triangle is equal to 1. So when we subtract it, we get a value for this function of 3. And that is our final answer for the third one. So this question, super big on understanding what a definite integral represents for a function, how we can relate it to area, and then also some useful tricks like flipping the bounds and negating the value of the function. So overall, solid question. Hopefully we did pretty solid on part A. Normally it only gets harder from there, right? So let's move on to part B. So part B says for the function g defined in part A, find all values of x in the interval from 0 to 6 at which the graph of g has a critical point, and give a reason for your answer. Part B. You know that g of x, as we wrote before, is the integral from 0 to x of f of t dt. Okay. Now it's asking for a critical point, or a critical value, of g. We know that critical points or critical values happen when our derivative is 0 or undefined. So we need to take the derivative of g. So the left side we get g prime of x. On this right side, we are going to use the second fundamental theorem of calculus that tells us when we're integrating from a to x of a function, this, when we take the derivative of it, we will just get the function evaluated at x. So our derivative of g is just the value of the function. So we're looking for where this is 0 or undefined. We're only looking from 0 to 6 too, which is a good thing to notice. And we see at x is equal to 4, f of 4 is equal to 0. So therefore, there is a critical point because the derivative of g is equal to f of x, and f of 4 is equal to 0. So that is our critical point. So pretty simple, not a super difficult part. So that one was worth 2 points out of 3, or 2 points out of 9 total. So we're at 5 out of 9 so far. And finally, we are looking to part C. So for part C, I'm kind of fully anticipating a really difficult question because it's worth 4 points. Not expecting it to be a layup, but here we go. Part C says the function h is defined by h of x is equal to the integral from -6 to x of f prime of t dt. It asks us to find the values of h of 6, h prime of 6, and h double prime of 6, and show the work that leads to our answers. Great thing is we always show our work, so it'll be free. So let's work on this problem. I'm going to start with h of 6. So let's do it. H of 6 is equal to the integral from -6 to 6 f prime of t dt. So if I want to evaluate this integral, I know I need to take the antiderivative of f prime of t, which is just f of t, right? We're going to evaluate it from -6 to 6, which is f of 6 minus f of -6. F of 6 is -1, just looking at our graph, and f of -6 is equal to 0.5. So when I subtract those, I will get -1.5 as my value for h of 6. So boom, 1 down, 3 to go. So let's look at the second one, h prime of 6. And I think this first one actually gave us 2 out of the 4 points. So we're living large. But h prime of 6. So first thing we need to find is h prime of x, right? Then we can just plug in x equals 6. And we're looking good. So to take the derivative of this function, I can use that second fundamental theorem of calculus. We know that h prime of 6 will equal f prime of x. So therefore, h prime of 6 equals f prime of 6, which is just the slope of the tangent line at that point. And kind of making an estimate, doing some rise over run, when we rise 1, we run 2, and we're going in the up and left or down and right, so it's in the negative direction. And I just found this -1/2 by looking at the slope of that line, right? Because we know it is a linear line, so our slope or our derivative is constant from 0 to 6, right? And it is equal to -1/2. You could write it as a decimal if you didn't want to do a fraction and a decimal in the same answer. But yeah, now we gotta look at finally the second derivative. So h double prime of 6. Now we know that h prime of x is f prime of x. So our second derivative of x will also equal our second derivative of f of x, right? So now we're kind of in this spot where we don't really have a way to solve for a second derivative because we don't have a value of a function. But there's an important thing that we talked about earlier, in that our derivative is constant, right? We said that from 0 to 6, f prime of x will equal -1/2 for all values from 0 to 6, right? Because it's a line, so our slope is constant, it's -1/2. So if I take the derivative of both sides, I get that the second derivative is 0 because my slope is constant. So therefore, because the second derivative of f is equal to 0 at all points x, h prime of 6, or h prime of x from 0 to 6, will also equal 0. And that gives me my final answer, giving me these three values, h of 6, h prime of 6, and h double prime of 6. So this is how I would approach this question. This is like a super classic question where they give you a graph and ask you to do a lot of interpretation with integrals, derivatives, just based on one curve. I think it's a really, really great practice question for us. And it would not surprise me if something super similar to this showed up on the 2025 exam. But That is all we got for today. I hope to see you again very soon. Happy practicing. Have a fantastic day.